Today we're going to look at catalysts and other ways to increase chemical reactions rates. Most of you know how a catalyst works, that the catalyst speeds up the reaction, but a lot of people forget the second part, which is that it does it without being consumed in the reaction. All right, so since most of you know what a catalyst does, I'm going to focus on how the catalyst does what it does. All right, so we've seen this energy profile before where we have the reactants on this side, so we'd say these would be my reactants. And over here on this side I would have my products. Now the chemical reaction we're actually looking at here is the decomposition of hydrogen peroxide to water and oxygen. Okay, you can do the balancing of yourself. The only problem here is that this should be water here. So actually I think it should just be a 2 here for the balancing and a 2 here. But that's the reaction we're looking at. So the catalyst, what it's going to do is it's going to speed up this decomposition. It's going to make it go faster. Okay, so we start with our reactants and we end with our products. So this red line represents the activation energy. Okay, so that would be the activation energy before we add the catalyst. So this would be my activation energy here for the uncatalyzed reaction. So in order for hydrogen peroxide to produce the water and the carbon dioxide, or the water and the oxygen, has to overcome this activation energy, and then it produces the products. So what the catalyst does is it provides a new pathway. Don't worry too much about this part here, what the reaction is. It's not important at this level, but what they're doing is they're adding hydrogen or hydrobromic acid, or HBr is what they're adding to this. So the catalyst that they're adding is HBr. All right, and the HBr is being put into this solution of hydrogen peroxide, makes the reaction occur faster. So the reason why it works that way, or why it does that, is that because these two steps here, and this is going in multiple steps, and this is something you should also be aware of, that this is a two-step problem. Okay, this would be a multiple step reaction. So we're just saying that this reaction happens in one step. Here we're saying it happens in two steps. But it doesn't matter, because both of the activation energies for these two steps are a lot lower than the overall activation energy for the original step. So that's what happens with the catalyst. Catalyst, what it's doing is it's making the reaction go faster by causing the activation energy to go down. Now, we're not going to get into this too much, but if you write the rate law is equal to K, and we talk about hydrogen peroxide's decomposition here, it might be to whatever power we would find experimentally. Again, in order for this rate to change, something has to change in our rate law to make this happen. And that what's going to change when we change the activation energy is we change the value of K. So again, K is going to be changed when we change the temperature, or if we change the activation energy. Okay, so and there's other things that go into the value of K, but for us at this level, this is pretty much what you need to know, is that when we change either one of these two, we are changing the value or the magnitude of K, which will then change your rate. Okay, all right, so simply put, the catalyst doesn't directly lower the activation energy of the original reaction. It supplies a new pathway, and that new pathway provides a lower energy to go. So just think about going, you know, up a hill. There's two hills you can go up. You can go up the large hill, or you can go up the small hill. Well, it makes more sense to go up the small hill because it requires less energy. So if the reaction has a choice, it's going to always go towards the lower activation energy. So it's not really changing the original. An activation energy is unique to a particular reaction. So hydrogen peroxide's decomposition has a particular activation energy, and that's not going to change. What we do is by adding a catalyst, it changes the steps. The actual steps of going from reactants to products literally changes, and those new steps are what gives us the overall change. So again, you have that original step here, and then you have that catalyzed one that's lower, and that doesn't always have to be in 2 bumps, it could be in 1, but the catalyzed. Now if you're going to sketch one of these, by the way, what you should probably do, because you won't have 2 different colors, you should probably do this in 1 color. Now let's do it again. Let's do this in blue. So what I would do is I would say, okay, here's my catalyzed one, or I should say uncatalyzed one. So I'm pointing to this one saying that that's uncatalyzed. And what I would then do is I draw in my catalyzed one. If they ask you to show how does a catalyst affect the rate of the reaction, then show here that this is the catalyzed one. Okay, and this here we have potential energy of the reaction, and you have reaction pathway down here. It's always a good idea to label your X and Y axis. So you would just show that before. Now if I draw it this way, my reactants start here, my products are here. Hopefully you can tell that this is an endothermic reaction. This would be endothermic because your reactants start out lower than your products end. So you're adding energy to get to the products that would be considered endothermic. All right, so enough about catalysts, I think. Let's see what the next slide. Oh, actually one thing. Homogeneous, heterogeneous, and enzymes. Homogeneous just means that the catalyst is in the same phase as all the reactants. So if you have liquids and you put a liquid catalyst in, homogeneous. Heterogeneous means that it's a different phase, and typically it's a different phase. I mean, a lot of catalysts are like this. A lot of them are metals that you tend to add to things, which, iron in your blood acts as a catalyst for the decomposition of hydrogen peroxide. It's something else you could use. But anyway, that's your homogeneous, heterogeneous. Not too many questions. I don't think you're going to see much of that. In biology, you probably talked about enzymes. And enzymes, a biological catalyst. So you have your substrate and the enzyme comes in and it fits into the receptor site here, creates this enzyme substrate complex that then changes your substrate into the products, and you end up with the products afterwards. So it only works when it comes in contact with the enzyme. So this would be an example of using a catalyst in biology. So you have your reactant here and your products down here. Same exact pattern, same thing we just saw before. Okay, the last thing I'm going to leave you with are all the ways that we can speed up a reaction. We can increase the concentration, and don't forget to be able, if they ask you to explain these, you must cite the collision theory. So you've got to talk about something with the collision theory for most of these. So increased concentration, we increase the number of collisions according to the collision theory. Increasing temperature, we increase the collisions and the kinetic energy. So the collisions go up and the kinetic energy goes up. So therefore, they collide more often and they collide with more impact, with more kinetic energy of the collision. So therefore, the reaction is going to go faster. We add a catalyst that changes the pathway. So we have a new pathway with a lower activation energy. So let's just do collision here. Just to put this in words here, it goes up. Okay, so collisions go up. Here, kinetic energy goes up and your collisions go up. So both of those. So that's why sometimes increasing the temperature is a little bit better than increasing the concentration if you have a choice. But it depends, because sometimes you can't increase the temperature because you might kill the biological system that you're trying to, have the reactions occur. And a lot of times with medications you can't do that. Or if like aquatic systems and you're trying to get something to happen in water, you don't want to kill whatever living system it is. So temperature might not always be key. That's why a catalyst comes in, because catalyst doesn't change the kinetic energy and it doesn't change the collisions. It lowers the activation energy. Lower activation energy by way of new pathway. Okay? And the last one is increasing the surface area of the solid. So if I have a solid chunk, according to the collision theory, picture this as a three-dimensional block. I'm not going to draw in 3 dimensions, but the only place that the reactions can happen is on the surface of the outside, right? So it can only get the reaction to happen on the surface. But what if I were to come by and split this into pieces, like I cut this in half, or cut it into 3 pieces here. Now I got these 3 long pieces now. I'm exposing some more, so now what I can do is I can now react on this side, on this side, on this side. I'm opening up more surface area for the reaction to happen. So the smaller that I can make those pieces, the more surface area I can expose, and therefore I can get more reaction to happen. So that's why to have the particles in very, very fine particles really makes for a very, very good reaction. Hence why gases are great for chemical reactions. The process of burning, in order to burn anything, has to be in the gas phase. So what happens is a solid has to melt to a liquid, then to a solid, and then it will start to combust in the gas phase, because that's where it's going to readily start to burn. That's why when you first start to light a candle, it doesn't burn right away, because you got to melt the wax down, and then you got to vaporize the wax, and then you can get the flame to happen. So anyway, so that's enough about kinetics. That's the end of this chapter, and I will see you guys in class.